These are the notes for section 3.7. It's the second day of optimization, which is day 12. Because these tend to be a little bit more challenging, there's only 2 slides, and I've decided to use the Star Wars pointer to help us out. So question number 1 says, a person in a rowboat 2 miles from the nearest point on a straight shoreline. Each of these are color-coded to the diagram here. So I drew a boat, and your boat will probably won't be as good looking as mine because I have decades of experience drawing 2 miles away from a shoreline, wishes to reach a house 6 miles farther down the shore. Down the shore means that from perpendicular to the boat, I'm going to walk 6 miles down the shore that direction. If a person can row at a rate of 3 miles per hour, that's a rate, 3 miles per hour, so it's a length with an arrow on it indicating it's a rate. And in terms of calculus, that's a dx dt or a dy dt. Since it's at an angle, I'm not going to label it dx or dy. It is a rate. And then finally, walk at a rate of 5 miles per hour. You're going to walk along the shoreline. This would be a dy dt, but this question isn't going to use that kind of stuff yet. So just keep that in the back of your head. Find the least amount of time. So the optimization means maxes and mins. We need to find a function for time and then find the minimum. So now that I have this diagram drawn up, the question is, where am I going to have the boat hit the shore so that we can maximize the speed that we're traveling or minimize the amount of time it takes us to get there? So a summary of stuff, we need a t function for time. We want to minimize it. We're given 2 miles and 6 miles, which are distances. We're given 5 miles per hour and 3 miles per hour, which are rates. But the question asked about time. What's the relationship between time, distance, and rate? It's right here. Rate times time equals distance. So a time function is distance divided by rate. So all we're going to do is we're going to set up time is the time in the water plus time on land. Since time is distance over rate, distance over water over rate over water plus distance over land divided by rate over land is sum of the 2 times, okay? So the last thing, and this comes from experience, so I don't know if we'd expect you to come up with this on your own, but once you say the boat is going to head for the shore at a certain angle, there's going to be a certain amount of land that the boat doesn't, or that the person doesn't walk along. So once they reach land, they're going to walk along this length here, but we're going to call this x. And the reason is because this makes up a Pythagorean triple or a right triangle, so I can say that x squared plus 2 squared is this green distance. Now we already have it labeled with miles per hour, but that's a green distance. So this distance is the square root of x squared plus 2 squared, which is right here, divided by the rate in water, which is 3 miles per hour, plus this distance, well, that's going to be the 6 miles minus the x length that we didn't need to walk along because we were using that when we travel along the water. So it's 6 minus x divided by 5. And there's our function. So I didn't hide it, but sheet of paper, take it out and take the derivative of this, set it equal to 0 and try and find critical numbers. Pause the video and figure that out. Okay, so like I said, I didn't hide it, so I have no way of knowing whether or not you tried it. First derivative, I turn these into exponents, so x squared plus 4 to the 1/2 means that the 1/2 drops down, negative 1/2 remains, and don't forget about the chain rule. Take the derivative of x squared, which is 2x, and then this is just, it's not the quotient rule, it's just negative 1/5 x. 6/5 is a constant, negative 1/5 x is a derivative of negative 1/5. Okay, simplify a little bit. Set this equal to 0 and solve. That's basically bringing the 1/5 over to the other side. Square both sides, and you get this stuff. You need to check your answers. Anytime you take a squared equation and square both sides, you could get a false answer. 3/2 works in this equation. Negative 3/2 does not. If you think about it, negative 3/2 in the top is going to produce a negative fraction because the bottom is always positive. This negative fraction will never equal a positive fraction, so that's not a critical number because it doesn't really solve that equation. Set up your first derivative test number line. 3/2 is here. I tried 0 and 2, plugged it into the derivative. I got negative and positive. I showed a little bit of work here. Because the function goes from decreasing to increasing, I know that I have a minimum. Once I find out the input for the minimum, I go back and look at the question. Find the least amount of time. I solved for x, which means now I have a mistake, so I'm going to need to fix this. This is not 3/2 of an hour. This is 3/2 x is a mile, 3/2 of a mile. So I would take and plug 3/2 into the time function up here, and the time at 3/2 is whatever you get when you plug in 3/2 to the two locations. And you have a calculator and you figure out what that is. So that's the first one. So the second problem here says find the maximum volume of a right circular cylinder that can be inscribed in a cone of altitude 12 centimeters and base radius 4 centimeters if the axes of the cylinder and the cone coincide. So what's happening is this is just a pure geometry problem. And here is the completed diagram, but I'm going to take a few seconds to try and help you figure out how to draw this on your own. So first thing they say is right circular cylinder that can be inscribed in a cone. So to draw a right circular cylinder, it's like drawing a soup can. You start with an oval at the bottom, go straight up, kind of straight, oval at the top. And what actually happens is that this stuff back here should be dotted because you can't really see that, the soup can, you can't really see that backside. So that's my right circular cylinder. The dimensions are height, so you go from center to center, up and down, and radius right there, okay? Next step is to draw the cone that's circumscribed around that. So I'm going to change colors and say that the cone needs to hit at those two spots there, okay? So I'm going to start way up here, come down, and what's going to happen is that the floor of the cone should match the floor of the soup can or the right circular cylinder. So at about the same horizontal, draw this, and draw my dashed line back there, and so there's my cone, and it also has a height which is going to go right through there, and a radius which goes right through there. So I knew it would be kind of messy to draw freehand, so I have a pretty good looking diagram that was on there previously, but that's a little bit of practice in drawing three-dimensional stuff. I'm going to now try to erase all that, and we'll pick up with the problem. So I got the bad drawing erased, and I'm back to having the good drawing. So now we're going to label things. The cone altitude is 12, so top to bottom of the green is 12, and the base radius is 4, which means this green radius here is 4. And the right circular cylinder also has dimensions that we need to compare it to. It has a radius and it has a height. Okay. Question says find the maximum volume. So don't look at this stuff yet, but what we need is a volume function. The volume of the right circular cylinder is area of the base, which happens to be a circle, times the height. So you've got pi r squared times the height. So the question is, in order to take a derivative, I need either the r to turn into an h or the h to turn into an r. And how am I going to do that? I'm going to come back to my diagram and look for a proportion that I can set up. Now here's the final proportion, but where did this come from? I'm going to highlight a couple things here. So in the cone, I have a height here and a radius here, and to get a triangle, I'm going to draw this hypotenuse there, okay? Can I find a similar shape or a similar size in the right circular cylinder? Well, if I look very closely, I'm going to make my highlighting a little smaller here. I have a triangle right here. This, and this. Now by angle, or a bunch of different other geometry theorems that hopefully you learned, you could prove that those two are similar triangles. The problem is that the labels don't quite match up. While I have 4 and 12 for the base and the height of the right circular cylinder, sorry, for the base and height of the cone, I need this length here. So it turns out that if I call this radius of the right circular cylinder there, I know that that whole length is 4, so the base of the triangle is 4 minus r, which is right there. So that's kind of the tricky part. This, oops, I didn't want that. Let me erase that. This right here is that length there. And then luckily in that triangle that I have, the height is the same. So the height here is the same as the height of the right circular cylinder, so that's h. So now that I have a way of matching up h and r, I could solve that for h and replace it in my function up over here, get rid of this h so that I'll only have r's. So if I cross multiply, I get 12 times 4 minus r equals 4h. Divide both sides by 4, and I get h is the same thing as 3, 4 minus r. So now that I've got that done, I can pick this up and put it in right here for h. Distributing the 3, I got 12 minus 3r. And now I'm going to distribute, and I have a fairly straightforward polynomial function where I can take the first derivative. So I have a volume function. If I want to maximize the volume, I'm going to take the first derivative, set it equal to 0. Factor, I get two critical numbers, 0 and 8/3. Test numbers that are easy to use, -1, +1, and 3. Plug those in. If I plug in -1, my volume here is negative, and I would plug it into this line here. You're going to get a negative on the outside, positive on the inside, so that's negative. Plug in 1, positive and positive. Plug in 3, positive and negative. So I've got a function that, a volume function that decreases, increases, decreases, so the max occurs right here. So if 8/3 is the radius that produces a maximum volume, okay, radius is 8/3, then I'm going to plug it into my volume function all the way up here and find out that the maximum volume is 256 pi over 9, or roughly 89.4 centimeters cubed. So again, the hard part about these problems is setting up the functions that need to be maximized or minimized, but working backwards, the steps are, we were told that we wanted to maximize the volume. Start with a volume formula. If you've got too many variables, go back to your diagram and try and find a way of converting one variable to another, and it could be something like this, setting up a proportion. Get your function in terms of one variable, take the derivative, set it equal to 0, critical numbers, first derivative test, and you're off to the races. So that's it. You'll get plenty of time to practice these. See you